Hello everyone, myself Ashish Choudhury from IIIT Bangalore, and I will be talking about improving the efficiency of optimally resilient, statistically secure asynchronous multi-party computation. So here is the summary of the paper. In this work, we present a new protocol for asynchronous multi-party computation or AMPC. The protocol provides statistical security. It has the optimal resilience of t less than n over 3, where n is the number of parties involved and t is the maximum number of corruptions. Communication complexity wise, it requires the communication of order n to the power 4 times kappa bits of communication for evaluating each multiplication gate, where kappa is the statistical security parameter. The previous best statistically secure AMPC protocol with optimal resilience is due to Patra et al., where the communication complexity per multiplication gate is order n to the power 5 times kappa bits. So compared to the protocol of Patra et al., we get an efficiency improvement of theta n in the communication complexity. As a new technical contribution, we present a very simple and efficient protocol for verifiable asynchronous complete secret sharing or ACSS, which is of independent interest. So secure multi-party computation or MPC, as introduced by Yao in 82, is a fundamental concept in secure distributed computing. So the scenario is the following. We have a set of n mutually distrusting parties, and the distrust in the system is modeled by a centralized adversary which can control a subset of these parties. And there is an n-ary function f which takes the inputs of all the parties and say the function output is y. And the goal of any secure multi-party computation protocol is the following. We want to design a protocol according to which the parties would like to interact with each other such that following properties are achieved, namely the privacy of the inputs of the honest parties, correctness of the computation, independence of the inputs, which informally means that adversary should not be able to base the inputs of the corrupt parties based on the inputs of the honest parties. We need guaranteed output delivery, which demands that irrespective of the behavior of the corrupt parties, the honest parties always obtain the output, and the list can go on. So the standard way of defining the security of any MPC protocol is the following. We say that an MPC protocol is secure if it has the effect of emulating what we call as a trusted third party. Namely, the protocol should have the same effect as if the parties interact with a trusted third party by giving their respective inputs to the trusted third party who computes the function output and gives back the function output to everyone. So if our MPC protocol can emulate the effect of such a trusted third party, then we say that our MPC protocol is secure. So because of its central importance, the MPC problem has been widely studied in various dimensions over the last 3 decades. So some of the dimensions in which we can categorize the MPC protocols are as follows. So depending upon the type of communication, we can have either synchronous MPC protocols or asynchronous MPC protocols. Depending upon the computing power of the adversary, we either get cryptographic or computational security or unconditional security. Depending upon the type of corruption, we can have either passive corruption. Passive corruption means the corrupt parties follow the protocol instructions correctly. Or we can have malicious or Byzantine corruption, where the corrupt parties can deviate from honest behavior in any arbitrary fashion. So in this work, we consider the most powerful adversarial model, namely we consider a communication setting which is asynchronous. We assume that the corrupt parties have unbounded computing power, and that's why we cannot make use of any cryptographic tools. And we assume that our adversary is malicious. So now let me say something about the asynchronous communication model. So in the asynchronous communication model, the parties do not have a global clock. So each party has its own local clock and the parties are not synchronized by any global clock. And the communication channels among the parties can have unbounded delay. The only guarantee in the asynchronous model is that if any message is sent by a party, it will be eventually delivered to the intended receiver, but it can be delayed by an arbitrary amount. And because of this, since the waiting time is not known, a receiving party does not know how long it has to wait for an expected message because we don't have the notion of upper bound on the message delays. And due to this, an inherent restriction that is imposed in the asynchronous communication model is that a receiving party cannot distinguish between a slow party whose messages are delayed and a corrupt party who has not sent a message at all. Okay, that means if I consider the viewpoint of this receiver, and if the message M which it is expecting does not arrive, then it does not know whether the sending party has sent the message or not. In general, if you consider an asynchronous protocol involving n parties and where up to t parties can be under the control of the adversary, then no receiving party can afford to receive expected messages from all the n parties because otherwise the wait may turn out to be an endless wait because there could be up to t corrupt parties who may not send the expected messages. So the best that any receiving party can do is the following. It can afford to wait to receive messages from up to n minus t parties asynchronously, and as soon as it receives communication from up to n minus t parties, it has to proceed to the next step of the protocol. But in this process, the receiving party might be ignoring messages from t potentially honest parties. So the summary is that even though asynchronous network model captures our real world network like the internet more appropriately because in internet we do not have known upper bounds on the message delivery. There are inherent restrictions imposed in the asynchronous communication model, and that's why designing completely asynchronous protocols is very uh, complicated process. So the MPC problem in the asynchronous communication model was uh, introduced and studied uh, in the pioneer work of Benor et al. In 93 and 94. And there are some inherent limitations which are imposed on any asynchronous MPC protocol. So for instance, any MPC protocol suffers from the problem that it does not support input provision. What do I mean by that? It means that inputs of up to T parties may be ignored for computation. And that's why the revised goal of any asynchronous MPC protocol is to securely compute an approximation of the function f on inputs of up to n minus t parties, where the inputs of the remaining t parties are ignored for the computation. And that's why the corresponding ideal world functionality for asynchronous MPC is the following. So now we again have the scenario that we have a set of n mutually distrusting parties. Each party has some private input and we have an n-ary function f. But to model the fact that any real world AMPC protocol suffers from the problem of unable to provide input provision, the trusted third party cannot wait to receive the inputs of all the end parties. Rather, it waits for a set of core parties, which I denote by this fancy set C, where the cardinality of the fancy set C is n minus t, which is actually provided by the adversary. Namely, what we are saying here is that adversary can specify to the trusted third party the set of n minus t input providers whose input should be considered for the computation. And Why we are giving adversary the flexibility of providing the set of n minus t input providers? Because as I said that in the asynchronous communication model, the messages can be arbitrarily delayed, and the message scheduling is also under the control of the adversary. So adversary can decide what are the which set of n minus t parties or input should be considered for the computation. So the trusted third party, once it receives the inputs of the parties in the core set, it substitutes 0 as the input for the remaining parties outside the core set, and then it computes the value of the function f based on the inputs of the parties in the core set, and input being 0 for the parties outside the core set. And once it computes the function output y, it can send back the output to the respective parties. So the goal of any real world asynchronous MPC protocol is to emulate this asynchronous trusted third party. So the idea behind any unconditionally secure MPC protocol, including ours, is that of shared circuit evaluation, where we assume that the function f which the parties want to compute is abstracted and represented by a publicly known arithmetic circuit over some finite field. And the goal of the MPC protocol will be to evaluate each gate in a shared fashion. Namely, it will be ensured that each value in the computation, starting from the input values all the way to the output values, remains secret shared among the parties through some linear secret sharing, where the degree of sharing is t. So assuming that we are able to do this, because of the linearity property of secret sharing, evaluating the linear gates or the addition gates in the circuit will be non-interactive, whereas evaluating the multiplication gates will require interaction, and that's why the focus of any generic MPC protocol is to uh, ensure that how efficiently we can evaluate the multiplication gates. And that's why the communication complexity of any generic MPC protocol is typically expressed in terms of the amount of communication that will be required to evaluate the multiplication gates in the circuit. So here are the relevant results for unconditionally secure asynchronous MPC. Benor et al. In 93 showed that if we want perfect security, where all the security properties of MPC are achieved in an error-free fashion, then this is possible if and only if up to n by 4 parties are corrupt during the protocol. Whereas if we want statistical security, where even though adversary is computationally unbounded, but we are willing to uh, allow a negligible error in the security properties, then we can tolerate up to n by 3 corruptions. So in this work, our focus is on statistically secure asynchronous MPC protocol with the optimal resilience of t less than n over 3. And these are the relevant results in terms of bit complexity or communication complexity per multiplication gate. So the work of Benor et al. Gives a feasibility result because, as you can see, the communication complexity per multiplication gate is tremendously high. The work of Patra et al. Significantly reduced the communication complexity. In this work, we further improved the communication complexity of the AMPC protocol of Patra et al. By a factor of t time. So now let me discuss about the challenges which we face while designing any asynchronous MPC protocol with the optimal resilience of t less than n over 3. So the key primitive which is used in any unconditionally secure MPC protocol is that of n comma t Samir secret sharing. So Samir secret sharing is a well-known primitive which allows a designated dealer with some private input S to distribute shares among the n parties for his secret S such that if any t plus 1 or more number of shares are available, then the secret can be reconstructed. But if only t or less number of shares are available, then the secret cannot be reconstructed. And to share the secret, what the dealer can do is the following. It picks a random polynomial of degree t whose constant term is the secret which dealer wants to share, and this polynomial is evaluated at n distinct alpha values, and the ith evaluation of the polynomial is given as the share to the ith party. So this is a very standard primitive. This will work in the synchronous communication setting. But if we want to execute this primitive in the asynchronous setting, and that too in a setting where there are up to t parties may not follow the protocol instructions properly, then there are some inherent challenges. So the first challenge is that we cannot ensure that all the n parties have actually received the shares, because there can always be t parties who may not participate and get their shares. So that's why we can only get what we call as incomplete secret sharing, where only up to n minus t parties can confirm that they have got their shares. But the problem that we face with this incomplete secret sharing is that later, if we want to reconstruct a secret which is incompletely shared, then out of among the n minus t shareholders who have got their shares, t shareholders uh, might further decide not to participate during the reconstruction, and at the time of reconstruction we might be only having up to n minus 2 t shares available for reconstruction. So if we consider the optimal value of n equal to 3t plus 1, then n minus 2t is t plus 1. And among these t plus 1 shares which are now coming at the time of reconstruction, there might be t shares which could be given by the corrupt parties, which are not sufficient to do the standard error correction. And that's why we cannot use this incomplete secret sharing for performing shared circuit evaluation. So that's why we want to design what we call as asynchronous complete secret sharing. Here we have a designated dealer with some private input S, and we need a bunch of properties depending upon whether the dealer is honest or corrupt. If the dealer is honest, then we require that the secret S should be eventually shared with every honest party getting its corresponding share. Whereas for corrupt dealer, we want a verifiability property. Namely, if the parties output some shares, then it implies that there is some value S star which dealer has indeed properly shared among the honest parties. More specifically, the ideal functionality for the ACSS primitive is the following. We have the dealer, which provides the sharing polynomial to the trusted third party. The trusted third party verifies whether the polynomial which dealer wants to share has degree t or not. If its degree is t, then the functionality distributes valid shares to the respective shareholders. Otherwise, it gives bought as the share to the respective shareholders. So Beno et al. Gave a protocol for asynchronous complete secret sharing, but it was very complicated because it was based on a sequence of subprotocols here, starting with AICP all the way to ACSS. Patra et al. Significantly improved the ACSS protocol by getting rid of several subprotocols involved here. Our approach for designing ACSS is to get rid of the AWSS primitive as well from the protocol of Patra et al. So in the rest of the talk, I will be talking about incomplete secret sharing and how exactly we go from incomplete secret sharing to complete secret sharing. So in the incomplete secret sharing protocol, there is a designated dealer with some degree t polynomial which it wants to secret share. And the protocol ensures the following. It ensures that the secret or the degree t polynomial is shared among a set of parties W whose cardinality is n minus t. That's why it is incomplete. And this set W is called as the set of primary shareholders. And this incomplete secret sharing is two-dimensional in the sense that each primary share will be further secret shared among a set of n minus t parties. So for instance, in this case, I am demonstrating the protocol with n equal to 4 and t is equal to 1. So in this case, the primary shareholders are the first three parties. The first primary shareholder will also possess shares of its primary share R1, and each of those shares, which I call as secondary share, so R11, R13, R14 are the secondary shares of R1, and each of them is shared by the respective secondary shareholder. Signed in the sense they are information theoretically secure signatures. In the same way, the second primary share is also shared, and WT is the set of corresponding secondary shareholders. Each of them has given their respective signatures on the corresponding secondary shares to the primary shareholder P2, and in the same way we have the set W3. Each of this set of secondary shareholders is of cardinality n minus t. The set of secondary shareholders might be different for different primary shareholders, but the property of this incomplete secret sharing protocol will be is that if the dealer behaves honestly in the protocol by selecting the right polynomial and distributing the right information, then eventually all the honest parties will become primary shareholders. Namely, all the honest parties will be included in this set W. So I refer the readers to the paper for the description of this incomplete secret sharing protocol, assuming that we have a value which has been secret shared in an incomplete fashion. That means we have this W set and the WI sets. Imagine we have a party who is supposed to reconstruct the secret shared value. Then again, I am demonstrating the reconstruction assuming n equal to 4 and t equal to 1. The standard way of reconstruction would have been that each primary shareholder gives its primary share to this designated party, but to identify corrupt primary shares, what we actually demand here is the following. Each primary shareholder should submit the signed shares, namely the signed secondary shares, and this designated party, upon receiving those signed secondary shares, verified the signatures, and if the signatures are verified, then it interpolates secondary shares to recover the primary share. This procedure of verifying the signature prevents a potentially corrupt primary shareholder to reveal an incorrect primary share because the signatures cannot be forged. So the designated party who is supposed to reconstruct the polynomial can keep on doing this process till it recovers t plus 1 properly signed primary shares. And once it gets t plus 1 properly signed primary shares, it can interpolate them to recover back the dealer's signed polynomial or shared polynomial. So now let us see quickly how we can go from incomplete secret sharing to complete secret sharing. Again, in this protocol, we have a designated dealer with a t-degree polynomial, which it wants to submit share verifiably. I will again demonstrate everything with n equal to 4 and t equal to 1. The first step that dealer will do is that it will pick a random polynomial, which is a bivariate polynomial of degree t in both the variables, where the polynomial f of 0y is the polynomial which it wants to secret share. And then it computes a matrix of n cross n values, which are basically distinct points on this bivariate polynomial. And we call the points along the ith row of this matrix as the ith row polynomial, which will be of degree t, and the points along the ith column as the ith column polynomial, which will be of degree t. Now, if we take the constant term of the degree t row polynomials, then it is easy to see that basically they constitute summation shares of the polynomial q which dealer wants to secret share. So the goal of this complete secret sharing protocol will be to ensure the following. We would like the dealer to ensure that he has verifiably given the ith row polynomial to ith party that will ensure that ith party has obtained its corresponding share of the Q polynomial. For doing that, we ask the dealer to distribute the column polynomials to the respective parties. And the row polynomials are now secret shared through our incomplete secret sharing instances. Now, as part of the incomplete secret sharing instances, each party will receive a share of a row polynomial, but once it receives the share of the row polynomial, it performs the pairwise consistency check of the received share with its corresponding column polynomial, because ideally, if D is honest, then this condition should hold. So what I am saying here is that if I consider this party, then he has already obtained the second column polynomial here, and as part of the sharing instances of f1x, f2x, f3, fx4x, he will be getting these points, which should ideally lie on its column polynomial. So that's what the second party should verify and publicly announce. And the goal of the dealer will be now to find a common set of n minus t shareholders for all the n secret sharing instances. Say for instance, if dealer finds the party 1, party 3 and party 4 to be the common shareholders who have publicly verified the pairwise consistency of the shares of the row polynomial and the column polynomial, then it basically ensures that dealer has actually distributed the row and column polynomials properly as per a single bivariate polynomial. And such a set V of n minus t shareholders, common shareholders, is bound to eventually exist. So once such a set V is found, dealer publicly announce it, and then each of the row polynomials is designatedly reconstructed towards the respective shareholders. So f1 of x will be now reconstructed towards the first shareholder, f2 of x towards the second shareholder, and so on. So I refer to the paper for the full details. So to conclude, we have presented a new statistically secure AMPC protocol with a better communication complexity. Future work will be to close the gap in the communication complexity between synchronous and asynchronous protocols. A key technique which is used in the synchronous setting to get better protocols is dispute control and player elimination framework, which seems to be inapplicable in the asynchronous setting. And that's why to get better protocols in the asynchronous setting, we have to come up with new techniques. Thank you.